Okay, so I'm going to go ahead and start talking. Right. This is the 9 weeks that is generally taken up with trigonometry. Tyree, you need to take off your hat. Okay. I mean, after this 9 weeks, some of the things that we do use trigonometry, but the most concentrated, this is trigonometry, is this 9 weeks. And in our book, it's right over there. Go ahead.
Oh, it's your last class?
Yeah.
Where's my stuff?
Right here.
Oh, okay.
Yeah. Yeah. See you in a couple of days. In the book, that'll be 2 chapters plus 2 sections. That's what usually constitutes the trigonometry. As I remember, my memory could be a little bit faulty, but as I remember when I was in high school, I did Algebra 2 trigonometry. There was not a class in between Algebra 2 trigonometry and calculus, right? But I think our Algebra 2 trigonometry was a little more in-depth than what we do now. I think it was like 6 weeks. That's about how long. It was not 9 weeks. It was something less than that. And the truth is, it was plenty. I mean, I've got a degree in math, a couple degrees in science, never needed any more trigonometry than what I got in high school. Trigonometry is not like as big of a subject as calculus or algebra. It's a much smaller, very specific kind of thing. So the study of triangles is literally what trigonometry means, right? Metry is the study of, I wrote that wrong. What should I have written? It is not the study of, it's the measure of. Mainly what does a triangle have? It's got 3 sides, it's got 3 angles. So that's what we're dealing with when we deal with trigonometry. And they have a fairly good paragraph right at the beginning of the first section, which says, for many, many years, it was mostly a way to calculate relationships between sides and angles. Probably when we get up to the time frame, yes? Sure. Probably when you get up into the time frame when they first define the coordinate plane, right, that you can start actually giving every point in the plane an x and a y coordinate, that you can come up with a function, which is a trigonometric function. And trigonometric functions are very useful in modeling. Take, for example, my background, which is a meteorologist. I mean, the most important trig function or functions are sine and cosine, because what do their graphs look like? They look like waves, right? Sines and cosines go like this, right? We don't have any other kind of function that would just look like a wave that goes on forever. And when you think of things like temperature, isn't that what temperature does? Doesn't it go up and down forever? Right? I mean, we can make a polynomial like a quintic polynomial, then it would have 4 turning points, okay? But that's not forever, right? That might model a couple days, but it's not going to tell you what's going on forever. So you need to have some kind of a function that has a wave-like periodic nature, meaning it just keeps repeating itself over and over and over. So the trig functions are important for modeling stuff. Okay, so we're going to do 4 and 5 plus 6. I think the way it's probably going to break out, sometimes, I would say most of the time the people who teach pre-calculus break chapter 4 into 2 tests. That the first 4 sections ends up being a test, and then the last 4 sections ends up being a test. I think when I've done that before, generally that second test, which includes 4 more sections, ends up being more like a cumulative test on the chapter when we do it that way. So right now, what I've got programmed is to do the first 4 sections, and we'll do a test. And I think if you just lay it out like a lesson a day, and then a review, and then a test, then that leaves our quiz on the 5th and our test on the 11th. All right, so that's kind of the way forward. We have February, there'll be 1 holiday. March, no holidays. That's the big month, right? and then spring break right around the corner, and it all goes so quickly after that, right? So we really need to have a good couple of months right here, because you know what happens in April, May, and the little part of June, which is number one, the weather looks really nice out there, and you're a lot less interested in school. Number two, there's all the SOL and AP tests that are coming up, and they start to distract you from what you're doing. So you definitely want to have a good 9 weeks now. The first lesson that we're going to do is just basics about angles, right? It's not the trigonometry yet. We're going to get to that in the next section, but in this one, we're just going to talk about angles and talk about the different ways that you measure angles, which would be radians and degrees. That's water right there, Kay? And we will do some word problem kind of thing. So in geometry terms, right, we know what an angle is, right? An angle is two rays that emanate from the same point, right? A ray is a arrow that just goes in one direction, right? It's not like a line. So it starts here and it goes there and it goes there. Together that makes up this angle, right? Now, we may not have used this in geometry, but in terms of what we're about to do now, we think of one of the sides of the angle as an initial side, and then the other would be the terminal side. The angle is this in between, right? That's the angle. It's the opening between two rays, like that. Now, what we're going to do is we're going to take that angle and we're going to put it in the coordinate plane like this. Okay, so there's the two sides of the angle, right? The vertex at the origin, right there. There's the vertex. The initial side is always on the positive x-axis, right? That's the initial side. And then the terminal side will be somewhere out there in the coordinate plane. You can see that they've drawn this one here with the arrow that starts here and it goes around that direction. What do you call, when the arrow's going around like this, how do you describe it? It's counterclockwise, right? So counterclockwise is when we're going around that way. Clockwise is when we're going around that way. Or in weather terms, that's cyclonic, okay? Because the low pressure would be right there. Cyclonic, anticyclonic. Okay. So when the angle, I've been playing with this one, right? When the angle opens up, okay, you could see here, right, there's the terminal side. I can move it anywhere around this way, okay? Let's say that I put it right there. When you go counterclockwise to get to the terminal side, that's a positive angle. Positive is counterclockwise. Okay. All right. Let me do this. Yeah, think enough of this, right? Negative is when you go clockwise. Okay, now how many degrees are there if I went all the way around the circle? Right, 360 degrees, right? So here, what would the angle be if both the initial and the terminal side were in the same place? It's a 0. It hasn't opened up at all, right? If I go all the way around once, then how many degrees is it? It's 360 degrees, right? So we're going to call that, this you could either say that's 0 degrees or you could say that's 360 degrees. Okay, how much would it be if I went halfway around? That was wrong. If I went halfway around the circle then. Okay, that would be 180. Okay, that would be 180 if I'm going like that, right? Positive angle. What if I went a clockwise direction? It'd be negative 180 degrees. So this can be either 180 degrees or it could be negative 180 degrees, depending on which way you go around the circle. Okay, what if I go halfway between 0 and 180? I mean, we're all familiar with that angle, right? That's a right angle. So it's 90 degrees. And that makes sense because it's halfway between 0 and 180. Okay, blue. So this is 90 degrees. Okay, what if I went instead that I went like this? What if I went from here clockwise to here? It'd be negative 90, right? That's still a right angle, but this time it's going down. So that'll be negative 90 degrees. Okay, well, what if I went what if I started here and I go counterclockwise all the way around to here? As a positive angle, that would be halfway between 180 and 360, 270 degrees. Okay, and so there's 270. And it's the same way, what if, this is not working out near as well as I thought it would. I was losing sleep on this. Okay, what if I went in the negative direction? I went, there's negative 90, negative 180. What if I went all the way back to here? It's negative 270. So what that points out is that the terminal side could be in the same place, but not have the same value of the angle, right? When that happens, that's called coterminal, right? Coterminal angles have the same terminal side, even if they don't have the same value. Is that right? Okay. So what if we did this? I'm going to take the terminal side again. Okay, so I've already said there's 0, and going in a counterclockwise direction, that was 90, 180, 270, 360, right? Well, what if I keep going? What if I went not just one time around the circle, but one time around the circle and then another 90 degrees? 450 degrees, right? You have to go 360 plus another 90, that's 4. So we could also say that that's 450. Which leads to, you will be asked questions sometimes, like find a coterminal angle. How do you find a coterminal angle? Add 360, subtract 360, right? Because whenever you go around 360 degrees, you end up where you were before, right? So to find a coterminal angle in degrees, add or subtract 360. I mean, even these here, like 90 and negative 270, they're off by 360, right? If you said negative 270 plus 360, you would get 90. If you said negative 180 plus 360, you would get 180. So all these coterminal angles are off by 360 degrees. So positive and negative, degrees being, everybody knows the degrees. It's kind of the way the textbook addresses angle measure. They do radian measure first, and then they address degrees. But everybody's actually more familiar with degrees than they are radians, so we're going to do that first. Okay, now, here's the other way that we can measure an angle, which is going to be radian measure. And radian measure depends on the concept of, and this is, again, something that we did in geometry, which is if we had a central angle in a circle, right, which we would always say that's n degrees, then it could intercept an arc on the circle, right? That's the intercepted arc. So another way to measure how much the two sides of the angle are opening is not to measure the central angle in degrees, but how long is the arc that it's intercepting? Right? If it intercepts a bigger arc, then the central angle must be a bigger angle, right? So when for radian measure, we're going to measure in terms of the intercepted arc, not the central angle. Now, the thing is, the intercepted arc will depend on two things, the way that I've drawn the picture. One is, where's the terminal side, right? If I draw it farther apart, then you're going to intercept a bigger arc, the angle is bigger. But what if the circle changes size? Right? What if the circle is only that big? I mean, the central angle didn't change, but the intercepted arc is going to be less, right? Because the circle is smaller. Okay, well, when we define radians, we're very specific in what we mean. Radian measure is the length of the arc when the radius of the circle is 1. So if you have a superimposed circle here, the radius of 1, then whatever's the length of the intercepted arc, that's called radian measure, right? It's not any old intercepted arc. You've got to define the size of the circle. So, I don't like this. It's a little better. So we have to say r equals 1, right? When r equals 1, the length of the intercepted arc equals the radian measure of the angle. You know, so, I mean, just think of it. I mean, how would you measure the length of that arc? I mean, ultimately, if you had a cylinder or something and you wanted to know how long is the outside of the cylinder, you could take a tape measure or something and you could measure it, right? It's a one-dimensional kind of unit. You know, this, if our circle, let's say it's, if our circle is in centimeters, 1 centimeter, then this would be so many centimeters long, basically. It's a line. It's a curved line, but it's still a line that has a length to it. Okay, label circle. Let me see what I did here. Go back to this. Oh boy. Edit, copy, edit, paste. And now let me get rid of some of this stuff. That's easier than I thought. Okay, now, if the radius is 1, how long would be the outside of the circle? I mean, what do you call the length of the outside of a circle. But what's the name of that? It's a circumference, right? So this, if a radius is 1, the circumference formula is 2 pi times r, right? But if the radius is 1, right, for r equals 1, then the circumference is 2 pi. So it's actually, if we were measuring the length of the whole circle, it's 2 pi long. Well, again, if that's 1 centimeter, it would be 2 pi centimeters to go from here all the way around. So without playing too much with my terminal side, remember that if the terminal side is the same as the initial side, then you say it's 0. So you would say that that is 0. But if the terminal side is in the same place as, if you go all the way around 360 degrees, in radian measure, that's 2 pi, right? That's how long it is to go all the way around. So you could also say in radian measure that this circle is 2 pi. Right now, how far would it be if we went halfway around the circle? Yeah, I mean, half of 2 pi is 1 pi. So this could be a positive pi. Or what if we went in a negative direction? It would be a negative pi. Right? What would be halfway between 0 and pi? Pi over 2. Okay? And if I went the opposite direction, that would be negative pi over 2. Right? What if I went in a positive direction, right? If I went around, past pi, halfway between pi and 2 pi. What is that positive angle down here? 3 pi over 2. So if I went in a negative direction, that would be negative 3 pi over 2. So we said on the last slide, we said if you want to find a coterminal angle, add or subtract 360 degrees. Okay, that's in degrees. What about in radians? What are you going to add or subtract? To find a coterminal angle in radians, add or subtract 2 pi, right? That takes you all the way around the circle once. Plus or minus 2 pi, right, to find coterminal angle. So they have a kind of a, to me, kind of odd way of defining radians, but I guess it's okay, right? It says 1 radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius of the circle. So they're using a formula here, which we're going to see a little bit later, but basically they're saying when this thing is 1, right, if theta equals 1 radian, then S equals R. There must be what's in the numerator is the same as what's in the denominator. So that would be the arc length. If this is 1 radian, then these two have to be the same. To me, that's just not a nice way to look at it. But that is the one that they've got in the book, if you're looking at it. Remember, the way I would better say it is, right? The length of the intercepted arc when R equals 1. I guess actually I got this even goofed up. If R equals 1, it's R that equals 1. When R equals 1, then S equals theta. So the measure of the arc, that is the angle. right? So determine two coterminal angles, one positive and one negative for each one of these given angles. All right, so if the angle is 9 pi over 4, again, how would I find a coterminal angle? Add or subtract 2 pi. Okay, if we add 2 pi, right, this always comes down to fractions. Right? So in this case, since that doesn't have a denominator, we change this to be 9 pi over 4 plus 8 pi over 4, which is 17 pi over 4. Okay, that could be our positive, right? How would I find a negative? Because they said one has to be a positive, one has to be a negative. Subtract, okay? Let's see what happens there. I'm going to take a shortcut here. I already know that 2 pi is 8 pi over 4, so I'm going to subtract 8 pi over 4. And that gives me how many? Just 1 pi over 4, right? So that's just pi over 4. That is not a negative angle. It said find one positive and one negative, not add and subtract 2 pi. Do it again, right? And if you would have noticed 9 pi over 4 is more than 2 pi, then you would have probably found subtract once to get the positive and then another time to find the negative, right? Minus another 8 pi over 4 is negative 7 pi over 4. Okay, and so those are 2. Okay, what about the negative pi over 3? How do I find coterminal angle? Okay, let's add 2 pi. Okay, plus 2 pi. Okay, turn it into a fraction. Negative pi over 3 plus 6 pi over 3, which is how many pi's over 3? 5 pi over 3. Right, now we've got to find the negative. There's our positive coterminal angle. Find the negative. Subtract. Negative pi over 3 minus 6 pi over 3. How many pi's over 3 is that? Negative 7. So coterminal angles. Easy stuff, right? You all right, Jimmy? Morgan? Good. So remember in geometry, we had these concepts of complementary and supplementary angles. Do you remember what it was in degrees? Because that's how you dealt with it. What did it mean for two angles to be complementary? They add up to 90, right? And supplementary was add up to 180 degrees. Okay, in terms of radians, what would that be? Instead of saying 90 degrees, we would say, what did we, pi over 2 radians, right? And in terms of 180 degrees, supplementary, in terms of radians, will be pi radians. Now, one thing to keep in mind about the measure of a radian measure, it's a unitless number. The radian measure is a unitless number. Most of the time, it doesn't have anything follows. They may sometimes, like for pi over 2, it may say pi over 2, and then they'll write RAD for radians. But most of the time, you're not going to see RAD at the end. If you do, it's you know, you'll certainly understand what it means when it does, right? But if it doesn't say that, if it just says pi over 2, it's radians, right? Sometimes when it comes to angle measure. You could even get an angle like, and most of the time when we're using variables to represent an angle, they use Greek letters. Not all the time, but most of the time. I could say theta equals pi over 2. Okay, clearly that's radians. Theta equals 90 degrees. Clearly that's degrees, right? But what if it said something like theta equals 2? What is it? It's radians. If it's degrees, it has a degree symbol. If it doesn't have a degree symbol, it's radians, always. So, and there are, every once in a while, they'll put that in there. You might find it confusing. I mean, everybody, when they see pi, they assume that that means good. That means radians. But it doesn't have to be that way. Right? I mean, you can even say, theta equals pi degrees. Nothing wrong with that. I mean, what is pi degrees? 3.14 degrees, right? It's a little more than 3 degrees. But the thing that tells you that you're definitely in radian measure is there's no degree symbol. If there's a degree symbol, it's degrees. No degree symbol, radians. Okay, so converting from one to the other. So if we look at the coordinate plane, we had a bunch of different, let's just say on the axes, where we know what the angles were in degrees and in radians, right? We knew that this one was, this could be, let's say 2 pi in radians, and it could be 360 in degrees. This one could be pi over 2 in radians, or it could be 90 in degrees, right? This one could be 270 degrees and 3 pi over 2. And then this one was the 180 degrees, which is pi. So all of those coterminal angles given in different measures are equal. 90 degrees equals pi over 2. So these factors that we use to convert radians to degrees or degrees to radians, they're all using this one right here. Since 180 degrees equals pi, then we can use that to convert units. Right? If I want degrees to go to radians, right, then I multiply by pi radians over 180 degrees. Why? Because pi radians equals 180 degrees. That's like multiplying times 1. Right? This fraction right here equals 1. It's just going to change the way that it looks. If I wanted to go from radians to degrees, then it's flipped the fraction. Now it's 180 over pi. Again, I can do that. I can multiply it because that is, in the end, that is 1. So we'll do a couple of practice on that. So convert 60 degrees to radians. And notice that it says do not use a calculator. Do not use a calculator. So for the letter A, 60 degrees, what do I multiply by? Do I go by 180 over pi or pi over 180? Right? Right. Remember, if I did it like this, 180 over pi, then I would have degrees in the numerator on both. I wouldn't get the cancellation that I need, right? So that's why it has to be the reverse of that. It has to be pi over 180. Right? Now you've got degrees in the numerator, degrees in the denominator. They cancel each other out. And what your answer is going to be in terms of radians, because pi is in the numerator. Now, when it says don't use a calculator, what they're saying is you ought to be able to simplify 60 over 180 times pi. How many times is 60 going to 180? 3. So this is pi over 3. Okay, what about 320 degrees? What do I multiply by? Same thing, right? Pi over 180. Right, the degrees cancel. You do a lot of like converting of units in chemistry, don't you? Right, so it's the same kind of thing. Okay, so that'll be 320 over 180 times pi. And how much do we simplify that? 32 over 18 makes 16 over 9. Now, I think I've got it on the next slide, but I'm not sure. Let me see. No, I don't think I do. I think in the homework problems, there is a section that says just like this, don't use a calculator. There's another one that says use the calculator. Right? If it says use the calculator round to 3 decimal places, what it means is, okay, now put in the value of pi and just turn it into all decimal. So if it says don't, then don't. If it says round to 3 decimal places, that means just put in the value of pi. And use on the calculator, I probably don't have it open, but you know, you've got a pi button on there. You don't need to be saying 3.14 stop. Right? We have a button for that. Just a second. I'm going to get the, oh, that is up. Clear. Yeah, remember the pi is over here on the hat. So use that. When you're going to use pi, do that. Don't do 3.14. Now, the next one. Convert these to degrees. Okay, so let's say pi over 6. How do I convert to degrees? Is that 180 over pi or pi over 180? It's 180 over pi. I mean, again, we want to make sure that our answer is in degrees. So we need this degrees in the numerator. So that'll be the units of the answer. Okay, in this case, the pi's cancel. 6 goes into 180 30 times. 30 degrees. About 5 pi over 3. Times 180 degrees over pi. Right? Pi's cancel. 3 goes into 180, 60. And 5 times 60 is 300 degrees. Now, I don't think on your homework that it actually you're going to run into this next scenario, but it does come up in our trigonometry coverage sometimes that they actually give us angles that are not just degrees in whole numbers and decimals, right? That they use this kind of this and this. Do you know what those stand for? Not inches. This is degrees, minutes, seconds, right? You divide a degree is divided up into 60 minutes, and each minute, which is 1/60th of a degree, can be divided into 60 seconds, right? And that's what those mean. So this is degrees. This is minutes. This is seconds. I mean, and you could do it like, you know, this is 32 plus 47 over 60. And then this is 64 plus 32 plus 47 over 60, all over 60. But the calculator does have this in there. If you look on the calculator, right, and I can't see well enough on that screen, but if you look above the apse, it says angle, right? So if you go, right there's the apse. Let's say I wanted to put this one in 64 degrees. So I go 64, then I go to second apse, and the very first one, there's your degree. Right, so I say 1. Okay, now I need to find the minutes. Well, that was in the same place. So I go 32, second apse 2. Okay, now if you go back to that menu, you didn't see the seconds. The seconds is on, where is that again? It's above the plus key. It's at alpha, y equal, alpha plus. So if I go 47, alpha plus, there's the minutes, the seconds. So you can put all that in. If you come across a problem where they've used that, then just enter it in that way. You know, if you don't remember, just remember that it's got to do with angles. That was the first section that we did. I mean, this is coming from a page in the text. They show you how to do that. Be resourceful. Don't just stop. I mean, there was one problem, and it's probably still going to come up, where I think it had an angle, something like, it said 3 degrees, 15 minutes. And I think I had 2 pre-calc classes at the time. And one class, everybody just said, oh, can't do that, stop. I mean, in the next class, they actually were a little better about it. They just said, oh, I'll just put in 3.15. Well, that's not actually correct either, but it's probably accurate enough for a Roman. You know, what they say is, you know, the Greeks came before the Romans, and the Greeks were very much into getting everything accurate. Like they were into calculating pi to as many decimal places as they could, right? And they had a pretty good approximation of it. The Romans come along, and they're engineers. They just want to know that the thing that they build works. So they tend to, you know, just say 3.25. It works. Don't worry. You know, it took until the Renaissance before people started really getting, you know, accurate again about pi. So now you know where that is. Now, everything up to this point, is basic stuff. There's a fair amount of homework with it because there always is on the first section, which is kind of introductory. This is the stuff that we tend to struggle with the most. It's the end of this section here. And it is arc length. And we kind of already discussed this. In fact, we kind of looked at this same formula when they used it to define radians. They just had it rearranged a little, right? They showed us this, theta equals S over R. Well, that's just rearranging that formula right there. S is what you use for the arc length, the length of that piece of the circle. R is the radius of a circle, right? And it is not necessarily equal to 1, okay? And then theta is the measure of the angle, specifically in radians, not in degrees. If you're given it in degrees, you're going to have to convert it to radians so that you can use that formula, right? So that is an important. Theta is measured in radians. Right, they've got that little, if R is 1, then S equals theta. That's true, but we're using this for other circles, not just the one with the radius of 1. So S equals R theta. So here's the kind of a problem you'll get, and you do have some like this at the end of the homework. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees, as shown in the picture. So here, the 240 degrees is telling you in degree measure this angle, right? Is that what we need for our formula? Right, we're going to use S equals R theta. Are we plugging 240 into that? No, what are you going to do? You're going to convert it to radians, right? And the radius is given as 4. So S equals 4, and you could do this all at one time, right? That's degrees, so that'll be pi over 180. So I plugged in the 240, but then I converted it in the same formula. You could do that off to the side if you want, right? You could just convert it first, then plug it in the formula. I think they do it like this, right? And so now, you know, in the end, you could simplify this as a fraction, but you're going to want a decimal answer in the end anyways. I mean, you know, definitely things are ending with a 0, divide by 10. They're even numbers, but you can also just turn it into a decimal. 4 times 240 times second pi divided by 180. 16.76. And are there units there? Since the radius was 4 inches, the arc length is 16.76 inches. Is that right? Yeah. Okay. Now we up the ante. Okay. Besides just arc length that we're talking about now, we're going to talk about speeds, and specifically 2 different speeds. One of them is called a linear speed, and one of them is called a, what do they call it? Angular speed. So the linear speed is telling you in radians, like how fast are you tracing out the arc length per time, right? How fast is that changing? The angular speed is telling you how fast is the central angle in degrees changing, right? How fast is it going around, not how much arc length is it tracing, right? So it'll come more clear here. Notice that they've used here for angular speed a Greek letter omega, right? It looks like a W, like a lowercase w, but that is the lowercase omega. Right? So omega is the central angle divided by the time. The linear speed is the arc length divided by the time. Right? I mean, another way to look at it, like S equals R theta. That was what we had on the previous slide, right? If you divide both sides by the time, what you got is the linear speed equals the radius times the angular speed. So finding a linear speed clock, that's real world, unless you use a digital clock. The second hand of a clock is 10.2 centimeters long, as shown. Find the linear speed of the tip of this second hand as it passes around the clock face. Okay, so let's see. S over T equals R times so we have to find the linear speed. The linear speed is that right there. So what do we need to plug into that? We need to be able to know the radius. The radius is 10.2. That's given. And then we need to know how fast is the second hand going around. Okay. If it goes around once in radians, how far did it go? 2 pi, right? So, and how long did it take? 60 seconds. Let's see. I'm going to leave it in seconds for that. So we're going to say our S over T, linear speed, equals 10.2 centimeters times 2 pi over 60 seconds. So calculate. 10.2 times 2 divided by second, oh, what am I doing? Clear. 10.2 times 2 times second pi divided by 60. 1.07, let's say. And what would be the units of that? Centimeters per second. Okay, another. The blades of a wind turbine, that's a new problem. They didn't have an old version of the textbook. But the old textbook was like 2003 was the publishing date. I don't know if many of you have driven across the country and seen all these wind turbines some places. I mean, they just go on forever some places. Okay, let's see. The blades of a wind turbine are 116 feet long. There we go. The propeller rotates at 15 revolutions per minute. Okay, which would that be? An angular speed or a linear speed? Revolutions per minute. That's angular, right? I mean, it could have the same angular speed no matter how long that is, right? That wouldn't matter at all. So that's an angular speed. It's just telling you how fast is it going around. Now, that's not the same as saying how fast is that tip of the blade going around. Now that's something that would be measured in linear speed. What is this distance traced out divided by the time? Okay, find the angular speed of the propeller in radians per minute. So let's see. Letter A. 15 revolutions per minute. Okay, now we need to do some unit conversion like you might have done in chemistry. We want this to be in radians. How do I convert revolutions to radians? How many radians in one revolution? 2 pi. So multiply it by 2 pi radians per 1 revolution. And now that cancels, and you're going to get an answer in radians per minute, so to speak. So you're going to say this is 15 times 2, which is 30 pi. And not knowing how they did it, let's say I'll turn it into a decimal. Right? 30 times pi is 94.25. 94.25. Now remember, radians are not actually, is not a unit, right? And the angle measure in radians is a unitless number. So this unit here, it's not radians per minute. It's actually, you're just going to use the minutes. It's minutes to the minus 1. That's the only part of that which is actually a unit, which is the minutes, because radians are not a unit. I mean, again, look at this. S equals R theta. R is in, is a length. S is a arc length. They have the same units. That means that has to have no units. Okay, B. Find the linear speed of the tips of the blade. Okay, well again, the linear speed is S over T equals R times theta over T. But we just calculated the theta over T. That was the angular speed. So we're going to put that here. And then what else do we have to plug in? 116. So that will go right there. So this will be the linear speed equals 116 feet times 94.25 minutes to the minus 1. So 116 times 10,932. 10,900, I'm just going to round this off, 9033. And then what would be the units of that? Feet per minute. Remember that minutes to the -1, the negative exponent means it really flips to the other side. Feet per minute. Wow. Yeah, it almost doesn't seem right. I don't even have my book out. $116 feet. This is 4. That's what they got. I mean, just think of it like this. That is their answer. Now, is that a realistic problem? How many feet are in a mile? 5,000. That's like 2 miles. They're saying that this turbine is going around, and it in a minute, it's gone 2 miles. That seems a lot. My guess is that that's not realistic. I mean, I've seen those things going around. They don't look like they could be tracing out 2 miles in a minute. Okay, last thing, and this one, I don't remember if you guys do this. I don't know if you do this in geometry anymore. It used to be part of it, area of a sector. Right. So we already figured out arc length is like a piece of the circumference. Area of a sector is a piece of the area of a circle. I think if you did this in geometry, as the last time I taught geometry, we did this for the area of a sector. Area of a sector. Right? It was the area of the circle, which is pi r squared. Right? And then it was times the central angle in degrees divided by 360. Right? That gives you the fraction of the circle. In this formula right here, actually the angle's in radians, which, again, if you want this to be in radians, you would multiply it by 2 pi over 180, and you would see some canceling and things like that. But ultimately, you're going to get this formula. The area of just this piece of the circle is 1/2 r squared times the angle in radians. That's not right. 1/2 pi r squared. Okay, so we do a problem. A sprinkler on a golf course fairway sprays water over a distance of 70 feet, and it rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. So again, our formula is 1/2 r squared theta. So what do we need to plug in? We need to plug in the r, which is given as 70. And we need to plug in the theta in radians. Well, it's given to us in degrees, so what do we have to do? Convert it, right? So and since nothing's being squared or anything, I'll just do it all in the same step. 1/2 times 70 squared times 120 times pi over 180. That's our conversion factor to bring it into radians. And that is all plug and chuggable. 70 squared times 120 times pi divided by 2 divided by 180. 5,131. And what would be the units of that? If it's an area, the 70 was feet, square feet. Feet squared. and that's it. So the homework, like I say, up till a certain point, it's mostly just, you know, easy, basic stuff. You're doing the little calculations. It's the end problems you really need to be trying hard to get at, right? Don't just turn away from something, you know, involving arc length or speeds or things like that. Think harder about them. You can get them.